In this video we're going to look at calculating the relative atomic mass of an element. It's not unusual for naturally occurring elements to be made of two or three or indeed many different isotopes. In this question here we've got silicon, a sample of silicon that appears to be made of three different isotopes: silicon 28, silicon 29 and silicon 30. Now, to calculate the relative atomic mass, which is defined as the average mass of the atoms in a sample relative to 1/12 the mass of a carbon-12 atom, to calculate that relative atomic mass, what we need the percentage abundance of each isotope, and we need the mass of that isotope in the element. If we have that, and we've learnt this formula, the formula is percentage abundance of the isotope multiplied by the mass, and we put that in a bracket, and we need one of those brackets for every isotope. Now in this question we've got three different isotopes. Exam questions normally have just the two different isotopes, but they can have three. And what we need to do is we need to write out one of those brackets for each of the different isotopes, and between each bracket we need an addition sign. So percentage by mass plus percentage multiplied by the mass, percentage abundance multiplied by the mass. And we've got three different isotopes, so we need one final bracket, percentage abundance multiplied by mass. Once we've written that out, we need to divide it by 100. That is the formula we need. Now, if we don't know that formula, we can't do this question, so it's imperative that you learn that formula. Now, as long as we've got that, we just need to put these numbers in, and then we can put the numbers into a calculator. So 92.2%, that's the percentage, multiplied by the mass. The mass there is the 28, that's the mass of that particular isotope. So 92.2 multiplied by 28, that will be our first bracket. Plus, second bracket, 4.7. 4.7 multiplied by 29. And the final isotope, 3.1%. 3.1%, 3.1 multiplied by 30. Bracket that up. Let's make sure we get that addition in there. Divided by 100. Now let's plug those numbers into a calculator, and that should give us the answer. Let's see what happens. 92.2 multiplied by 28 equals 2,581.6. We've got brackets like this. It's really important we work the contents of the brackets out first. So I'm going to do a second bracket now. 4.7 multiplied by 29 equals 136.3, wasn't it? 136.3. 3.1 times 30. 3.1 times 30 equals 93. Plus 93. Let's divide all that by 100. Let's see what happens when we add all those together now. So 2581.6 plus 136.3 plus 93 equals, so we've got 2,810.9, and we're going to divide that by 100. So what we've done, we've just added those three together, and that's given us that number, and then we're going to divide that by 100 in a moment. So our final stage now, let's just divide that by 100. That should give us our answer. Our answer, 28.109, or 28.1 to three significant figures. And that's the answer to that question. As I said, these are fairly standard exam questions. What we have here, we have a past exam paper. This is Edexcel C2 from June 2015, high tier question. So we've got question, what is it? It's question 4. A part 4 here. So we've got a absolutely standard question here. A sample of copper contains 70% copper, 63 atoms. So I always think it's good to underline these things in exam questions, and 30% of copper, 65 atoms. So let's have a quick go. This is exactly the same as before. We need this formula here. It's exactly the same one. So again, you have to learn it. If you haven't learned this, you can't do the question. Percentage times mass. It's only two isotopes this time, so we just need two of the brackets, percentage times mass. We're going to divide that by 100. Okay, so percentage is 70%. 70% copper, and it's copper 63, 70 times 63, plus 30 times 65. 30 times 65. Now, it's always really, really good to be just having an idea of what the answer might be in your head before you start putting these numbers into a calculator, because it's so easy to make errors on the calculator. So the two isotopes that make up copper here are 63 and 65. So the relative atomic mass, the average mass, remember, relative atomic mass is the average mass of the atoms in the sample relative to 1/12 the mass of a carbon-12 atom. The average mass has to be between 63 and 65. Now, it's going to be closer to the one that there's more of. So there's more of copper 63, 70% of copper 63. So that's obviously going to have more of an impact on the average. So I would wager the average is going to be around about 63.5. Just looking at this, that's my guesstimate. Let's put these numbers into the calculator and see what happens. So 70 times 63, let's start with that. 70 times 63. Remember, we work the brackets out before we do anything else. 4,410 plus 30 times 65, 30. Times 65 equals 1950. All right, let's add those two together. Let's complete that first. Divided by 100. Let's add those two together now, and just to get a tiny bit closer to the finish. Plus 1950 equals. So that's now going to be 6360 divided by 100. Okay, divide that by 100, and the answer is 63.6. And we'll leave that 63.6 to three significant figures. Okay, and that actually works quite nicely with my guess, didn't I? I said my guess was going to be closer to copper 63, and I said about 63.5. So that's close enough now. I'm pretty sure I've got that in my calculator correct. So that is how we work out the relative atomic mass of an element.